Good day, my name is Carlos, and today I'm going to explain the paper entitled A Novel Methodology of Parametric Identification for Robots based on a CNN in the 8th International Symposium of Language and Knowledge Engineering. The content of the presentation is Introduction, the proposed methodology, a case study, results, discussion, conclusions, and references. The parametric identification is a highly relevant line of research due to the interest in knowing the behavior of a robot with a high precision. The most widely used algorithm to identify parameters is the least squares algorithm. However, the trajectory followed by the robot must be optimized for parameter identification. Neural networks are used as a complement, friction estimator, and compensation system for robots. Other applications are calibration of robots with a deep neural network (DNN) to measure the external force and for signal estimation. The proposed methodology of this paper has not been addressed yet. The survey 27 shows application of the CNN because of remarkable improvements. This work has two contributions. The first is a proposed methodology that identifies parameters of a robot avoiding trajectory optimization. Consequently, the required time for parameter identification is reduced. In addition, once the CNN of the proposed methodology was trained with a specific robot model, the algorithm can be scaled to identify multiple robots with the same model. The novelty of this work remains in the parameter results by a CNN, without an optimizing trajectory and the transformation of the robot signals into a small image that contains enough information to identify the parameters in a short time. The other contribution is the fit-right robot validation of the dynamic model by obtaining parameters using the proposed algorithm. Proposed methodology. First, a robot is following a predefined trajectory that is not required to be optimized. The measure acquisition systems gives only the position and torque signals of the robot. Therefore, a block of filtering, derivating, and subsampling is used to estimate the velocity and acceleration. Together with the torque, the motion signals are subsampled to enough length to be processed in a short time. Then the initial dynamic parameters P0 are initialized to create an image with the proposed transformation technique. Once the image made with the robot signal is obtained, the CNN finds the parameters residuals. A proposed evaluation metric analyzes the robot torque and the estimated torque. The output dynamic parameters are denormalized when the evaluation metric gives a value greater than PS. The developed neural network consists of 3 convolutional layers, 2 matchpool layers, and 3 feedforward layers shown in Figure 1. In Figure 2, the convolution operation of equation 1 is represented by an asterisk, the addition of the bias by a plus sign, and the Pulley layer by an R. The activation function for hidden layers is the rectifier linear unit function because of the property of avoiding the fading effect. For the output layer, the sigmoid function is used. Two transposer vectors are multiplied to obtain an image from the motion and torque signals. The first step is sampling the robot signals with the discrete cosine transform. The DCT can reduce the length of a signal to an integer as described in equation 3. The original signal is transformed and their frequency spectrum is cut to an ns length. The second step is filtering the signal with the filter of equation 4 and estimate the velocity and acceleration with the position as shown in equation 5. The third step is the creation of the image with vector phi and vector alpha as described in Figure 3. These vectors are different for each robot and their content is a function of the specific dynamic model of each robot. A repository of NS simulation of the dynamic model is generated to train the CNN. The trajectory used to generate the training data is a sinusoidal signal implemented by the proportional derivative position control with dynamic compensation of equation 7. The training process of CNN uses two types of image. AP image constructed with the dynamic parameters that match with the position and torque signals, and the M-in image that uses random parameters as shown in Figure 5. The evaluation metric analyzes the similarity between two signals in the time and frequency domain, where epsilon is set in 0.4 units. The proposed algorithms identify the parameters of a robot, introducing the robot signals. It's dynamic modeled, and the training is CNN. In lines 1 and 2, the derivative is estimated with the filter of equation 4, and then the equation 5 is applied to estimate the speed and acceleration. Lines 3 and 4 show the filtering of the position and torque. In line 5, the filtering signals are subsampled. In line 6, the variable v for the metric is initialized with zeros. The parameters are initialized by assigning NP numbers as shown in line 7. The while loop of the line 9 runs until the variable v exceeds a threshold Vs and identified parameters P0 are physically possible. Within the while loop, NP random numbers of range 0 to 1 are assigned to P out. The vector psi and alpha are determined in lines 10 and 11 to create an M image of line 12. In line 13, Mn is normalized to range 0 to 1, and it's introduced to the CNN in line 14. In line 15, the parametric residual PR is recovered by applying the inverse sigmoid function. In line 16, the identified parameters are obtained by subtracting PR from P out. The torque determined by P out is constructed with the dynamical model and the set of signal heads as shown in lines 17 and 18. The evaluation metric applied to T out and the input torque to determine their similarity. Finally, P out is obtained. A case study. The robot to be identified with the proposed methodology is a 2DOF fit-right robot. The robot uses 2 DC motors, 2 incremental encoders, and a vivid FPGA system to handle the robot. The microprocessor of the system is programmed via PC, as shown in Figure 7. The schematic diagram of the fit-right robot is shown in Figure 8. The motor gearbox torsional stiffness are represented by the gears, and their torsional friction coefficients are between the two of the gears. For the gearbox screw torsional stiffness, it is used a connection bar, and for their torsional friction, it is used a hollow bar. The dynamic model of the robot considers that the sum of the external force and reaction force is equal to the mass by their acceleration. The model of the robot is determined by the equation 9, where theta represents the variables for x-axis and phi for z-axis. The torque applied is by a PWM signal of the embedded system. To group the dynamic parameters of the equation 9, the deformation of the mechanical connection are considered less to the encoded resolution. With the set of equations shown in 12, C and alpha vectors are constructed with the 8 parameters as equation 13 shown. For this specific case study, the alpha vector is set as the torque. The main idea of the image construction for the fit-right robot is that when the identified parameters match the torque signals, the M image contains an approximation of the square value of the torque. The verification of the algorithm uses 5 simulations of the equation 12. The FPGA contains the programmed trajectory of equation 9, followed for the fit-right robot. Data acquisition from the fit-right robot is implemented with a Wi-Fi interface in LabVIEW. The raw data is transferred from the FPGA board to a personal computer to be processed by the identification algorithm. The processed algorithm was implemented in MATLAB with the optimized convolution in 2-dimension function, and the functions to handle the NVIDIA graphics unit. The data generation CNN trained and the algorithm runs on a personal computer. Results. The computer set for the parameter identification algorithm has a GTX 1060 GPU with an Intel i7 processor. The computational cost is determined experimentally for convolutional layers. The cost time of the CNN is approximately 3.35 milliseconds. Figure 10 shows the loss function for both training sets. The normalized Fourier frequency spectrum of the trained kernels is shown in Figure 11. It is observed that the kernels are different from each other, and each kernel in combination with the activation function determines the parameters of equation 12. The parameters used to identify simulation are described in the Table 1. The simulation S4 and S5 have parameters outside the range -1 to 1 to verify the denormalization step of the algorithm. Table 2 describes the results of the evaluation metric along with the execution time of the identification algorithm. The evaluation metric for the simulation signals has values that exceed 90% similarity. With the denormalization technique implemented in the proposed algorithm, it is observed that also the training data were created with parameters only in the range -1 to 1. The algorithm can identify parameters outside this range. The trajectory of the robot is shown in Figure 14. Table 3 shows the identification results of the parameters shown in equation 12 of the fit-right robot with the evaluation metric and the algorithm execution time. For both axes of the robot, the metric is about 90%, and the execution time is less than 1 second. Figure 16 shows the comparison between the torques of the fit-right robot and the torque obtained by the identified parameters. The proposed evaluation metric considers the slight variation of the signals to be compared. On the x-axis, even though the real torque is too close to the identified parameter torque, the similarity does not exceed 90% because there are high frequency difference with a small amplitude of the frequency part of the evaluation metric. In the zero-cross region, the characteristics of the proposed evaluation metric for electronic signals make it ideal for comparison because it considers the frequency spectrum. Discussion. Optimizing a trajectory to identify dynamic robots parameters takes time because its new trajectory needs to be tested on the real robot. With the proposed methodology, trajectory optimization is not necessary and the processing time is reduced. The processing technique applied to the input data can sample the signals to any integer value length. The transformation of the signals into an image does not require the frequency spectrum and has the necessary information in a simple way to be processed by the CNN to obtain the dynamic parameters. The proposed algorithm has a short running time. Once the CNN has been trained with one type of robot, it can be applied to any robot with the same dynamic model. Conclusions. In this paper has been presented an algorithm for parameter identification based on a convolutional neural network. The fit-right robot is used to test the proposed algorithm. The parameters extraction with the CNN and the creation of the image are the novelty parts of this work. For the image creation with robot motion signals, the proposed transformation technique puts enough information into a small image to determine the parameters quickly. The proposed methodology does not require the optimization step of a trajectory performed by a robot. Therefore, once the CNN is trained with the dynamical model of a specific type of robot, the algorithm can identify the parameters of any robot that uses the same model as the one used to train the CNN. Unlike correlation, the most used metric in parameters identification papers, the proposed metric analyzes the information in time and frequency. These characteristics make it ideal for comparing similarities of electronic signals such as the torque measurements. The simulation results show that the algorithm achieved a similarity greater than 90% because the simulation model was the same that was used for the CNN training. The results of the fit-right identification show that the similarity exceeds 90%. The parameter identification for these robots contributes to validate the dynamic model of 8 parameters. The results presented in this paper show that the proposed methodology works in the identification of dynamic parameters. Consequently, the future work will be the application of the proposed algorithm to identify other types of robots used commonly in the industry and investigations. Thanks for viewing this presentation. My name is Carlos.